Welcome to everyone. I'm Antonio Russo from Imidea Networks Institute of Madrid in Spain, and I'm here to present our work, Byzantine-tolerant distributed grow-only sets, specification and application, in collaboration with Vicente Cholvi, Antonio Fernandez Anta, Chryssis Georgiou, Nicolas Nicolaou, and Michel Raynal. In a recent line of research, the notion of distributed ledger and the blockchain used to implement it with Byzantine fault tolerance guarantees have been abstracted in the concept of the distributed ledger object, that simply is a sequence of record treated as an append-only sequence. The DLO have been investigated in order to provide its Byzantine fault tolerance specification and implementation. In the most general way, this formalism allows only two operations: an append to append a record to the sequence, and a get to obtain the whole sequence. In detail, its implementation relies on a black box Byzantine atomic broadcast system that provides two primitives, the broadcast and the delivery, ensuring four key properties. The validity, that says that each broadcaster's message is delivered also to the broadcaster. Agreement, that if a message is delivered at a server, it is eventually delivered to all servers. Integrity, messages are delivered at most once and only if they have been broadcasted before. And the total order properties, that ensures that messages are delivered in the exact same order to all servers. We asked, do we really need those strong properties in all the applications in which the BDLO, the distributed ledger, are used for? We focused on the total order property, and we took two main examples. First example that we took is the atomic append. With the DLO work, the atomic append problem has been formalized with two distinct users who want to append in an atomic way two records in two different ledgers, with the guarantee that either both are appended or no one is. The problem has been solved through the introduction of a central smart BDLO, in charge of taking the records of the atomic append and triggering with its own servers the respective appends on the target systems. We asked, it is necessary for the smart BDLO to rely on the strict ordering of the records A and B that come from users? Ordering in this case is completely indifferent. It is enough that the SBDLO has both records, whatever order they came from. Another example is the cryptocurrency use case. Let's say to have four distinct users who want to transfer among them a quantity of cryptocurrency. The two showed transactions are completely independent, and their ordering is completely indifferent, such that a ledger recording them in a swapped order would be absolutely equivalent. That's why we propose to formalize a new data structure. We started from the same distributed setting of BDLOs, in which we have asynchrony, so both processing and communication happen in a synchronous way. Each process can have a Byzantine behavior, and with the restriction that the maximum number of Byzantine failing servers is bounded and known. Communication channels are reliable, so no message can be lost, duplicated, or modified. Finally, all messages are authenticated, and the set of servers is always known, such that messages' authenticity can be always verified. So, our data structure, that we will call DSO, distributed set object, is a distributed set for which we define only two possible operations: the add, that includes an element in the set, and the get, that returns all the elements of the set. Defined in such a way, this is a grow-only set, and while there are other works that treat the possible usages and combination of the grow-only sets, our proposal deals with the possible implementation of such a data structure. In particular, what we aim to provide is a Byzantine-tolerant specification and implementation of a DSO. Let's start with the specification. Informally, in respect to all correct processes, the data structure must guarantee that all operation invocation eventually completes, and that all the add operation have an effect on the system state, such that eventually the added elements is included in all subsequent get. To implement the BDSO guaranteeing these two properties, we rely on the Byzantine Reliable Broadcast Service. That is a slightly weaker service in respect to the Byzantine Atomic Broadcast. In fact, it ensures these properties: the validity, that ensures that there is no message fabrication; the integrity, that there is no message duplication; and two termination properties, that the messages that are broadcasted are eventually delivered also to the broadcasters and to all processes. As you can notice, there is not any assumption on message delivery order that let this primitive result in not requiring any Byzantine fault-tolerant consensus algorithm for its implementation. Let's see how we propose to implement the Byzantine-tolerant DSO. We will call f the maximum number of Byzantine failing servers that can be tolerated by the system. This is important because this is the only assumption that client and servers can do in respect to all the other participating processes. The add operation for the client requires that the add request is sent to 2f+1 servers, and the client waits for f+1 acknowledgement from the servers. This ensures the client that at least a correct server correctly processed the request, and eventually the add request will be taken into account in the system state. On the server side, when an add request is received, a correct server calls the BRB broadcast primitive and waits for f+1 BRB delivery of the same request by f+1 different servers. This guarantees that the request was correctly issued following the algorithm. In other words, a correct server wants to be sure that an element that he is adding to his local set was not forced by Byzantine server colluding with a client that tries to broadcast that message without requesting it through the add protocol. When this condition turns true, the server adds the element to his local set and sends back the acknowledgement to the client. What should be noted is that these algorithms are not relying on any relative ordering among messages. In fact, the BRB primitives are not running any consensus algorithm to implement the broadcast and the delivery. When issuing a GET request, most of the logic is in charge of the client. In fact, a client is required to send the request to 3f+1 servers and wait for 2f+1 responses. Then, it will return a set whose elements are present in at least f+1 distinct responses. This ensures the client that each returned element was correctly processed by at least one correct server. Note that this does not mean that the element is definitely included in the DSO. In fact, if the server to which the GET request is sent is not the same, it can happen that the element did not spread yet to the whole network, and the GET does not return the element. On the server side, a server is only required to respond with the local set SI that he holds. Once defined the two key operations of the Byzantine-tolerant DSO, let's see what are the benefits of such data structure, and let's go back to our two examples. In the atomic append scenario, the third trusted party that was in charge of solving the atomic append problem is no longer in charge of running a Byzantine fault-tolerant consensus algorithm. In fact, we can leverage the BDSO implementation to gather the records for the atomic append from users without caring about their relative ordering, and then trigger them on the target PDLO. Similarly, even if the target systems are not ledgers but other DSO, we can define the atomic add problem. The problem setting and its solution remain quite unchanged, with a trusted distributed third party that only needs to collect required elements without considering their relative ordering. Then he can add the relative elements to the target BDSO. Let's make a small step over and think if we can use the BDSO to implement a data structure with slightly stronger guarantees. Suppose that we do want to have ordering among elements, but elements can be issued only by a single writer. This is very similar to the cryptocurrency case in which only the coin holder can spend his own money. We can take the same property of the DSO, match them to the DLO sequential specification, and add the Byzantine strong prefix guarantee to consider the total order property among elements. Let's see how our algorithm changed to achieve such a data structure. In order to implement the consensus-free single-brother BDLO in the eventual consistency fashion, say def the Byzantine server tolerance and n the total number of servers, the client is in charge of maintaining an element counter to add the ordering information to the element that he wants to append to the sequence of records. The request is sent to floor of n plus f divided by 2 plus f plus 1 servers. This is a constraint put by the server algorithm. We will see why. Client waits for f plus 1 acknowledgements in order to be sure that at least a correct server successfully processed the request and the element will be eventually included inside the data structure. On the server side, the request is BRB broadcasted like in the BDSO only if the sequence number contained in the request was not already broadcasted before. Then, server waits for floor of n plus f all divided by 2 plus 1 delivery of the same request by different servers. This number of requests ensures that two conflicting requests containing different elements but the same counter cannot be sent to disjoint sets of correct servers, returning both a success outcome, but at least a correct server must process both. Since we imposed that a correct server do not broadcast elements containing counters it already broadcasted, then the set of correct servers cannot diverge in different states because of this malicious behavior. When the required number of BRB delivered is received, then server can send the acknowledgement back to the client. In the camera-ready version of our work, the server algorithm in step 2 had to wait for a higher number of requests spread by different servers. It was floor of n divided by 2 plus f plus 1. And we recognized that it was too much to ensure what we want to provide. So we load that number to floor of n plus f divided by 2 plus 1. And this allows to set the minimum number of servers that are needed to implement the single brother BDLO from 4f plus 1, like we wrote in the camera ready, to 3f plus 1. In this way, we're able to ensure optimal resiliency also for this data structure. Note that there is not total ordering with the BRB broadcast and the BRB deliver, so there is no guarantee that a request sent to a server is delivered to all servers in the exact same order in which it has been broadcast. When processing a GET request, again, most of the logic is in charge of the client. In fact, he needs to send requests to 3f plus 1 different servers and wait for 2f plus 1 responses in order to have at least f plus 1 responses to process. In this case, each element is returned if it is present in f plus 1 distinct responses in order to ensure that at least one correct server processed the request, but also an element is returned if it has the previous one in the sequence except for the first one. That is always returned. In this way, only a continuous sequence of records is returned, and the Byzantine strong prefix property is guaranteed to be valid among different GET requests, also issued by different clients. And eventually, all the records will be included in the sequence. On the server side, server is only in charge of responding back with the local set that he holds to the client. To summarize, we presented the DSO specification and its Byzantine fault-tolerant implementation. Then, we used it to solve the atomic append and atomic cut problems, and we provided a modified version to implement an eventual consistent single-rider BDLO, free from the constraints of implementing and running a Byzantine fault-tolerant consensus algorithm. Our next step regarding this work will be to provide an implementation of the BDSO and the eventual consistent single-rider BDLO in order to benchmark them and compare them with similar solutions. Finally, we will try to implement a cryptocurrency leveraging these two data structures. For any doubts and considerations, feel free to contact us at these addresses. Thanks for your attention.